Yeah, hi, good evening. So welcome to the B10 of the session today. So, am I audible?
Yeah, you're audible.
Okay,
Good evening, sir.
okay. Okay, so this is week 10, and that professor have discussed regarding some optimization in the embedded system. So, how we can achieve the optimization things. So, some related things are also discussed. So, have you watched the lecture that week 10? Have you seen?
Mm, Week 9, I have watched, not 10 actually.
Oh, okay. So this is week 10, no? This is week 10 running. Okay. Last Friday, actually, week 10 released. Yeah. So, still, okay. So, if you have any specific doubt, or can we start uh, things? So, like week 10, okay. So, regarding this optimization, so I hope you are aware of this algorithmic optimization thing. So, what is this concept? So this is the one optimization we can do in our the embedded system programming. So what is that? And we will discuss this thing today. And I have another topic that practical scenario. I have one another thing. So as I mentioned in the last my session, so that we will discuss some driver development process on the physical board, how we can develop the driver. Okay, so that things we will also explore a little bit. Okay, so I'll start with this optimization thing. So Professor, I'm sharing my screen first. So after that, yeah, I hope my screen is visible.
Yes, sir.
Okay, so one second. Let me check the slides of it. So this is regarding the efficiency. Okay, so this is the title of the Big Ten. How we can make efficient embedded system. So in the efficiency, Professor have discussed some topics of this interrupts and polling. So what is this actually? So interrupt, we can make efficient our code. So you know that when we write any code, okay. So when we write any code for our the embedded system, so we run our that code inside the loop, okay. And inside the loop, you can see uh, so like this condition. So we are discussing first polling mode. So polling mode is basically we mention some condition and inside the while loop. So everything is runs inside the while loop in the code. After that, we check some condition. Okay, inside the while loop, we check some condition, and based on the condition, we perform our logic. So perform our task. So that condition is actually, so this is iteration continuously, it is iterating. Okay, this loop is running, and every time we are looking some value of the registers in our embedded system. So every time we are just in every iteration we are checking this. And once if we found any specific value which we have set in our code, so that at that time we perform some action. Okay, so in this way, that means our CPU is continuously busy to do something. Okay, so that means our CPU is completely busy in iteration, and every time it is checking some value of the registers, and based on that it is taking some action, it is deciding some action. Okay, so like this is this some code is given for just LED state. Okay, so we are checking some pole mode, and based on that we are performing the we are changing the LED state. So in this way, this concept is called as a polling method. So continuously we are checking the condition in the iterations. So how we can make this efficient? So what we can do, uh, we can use the interrupt thing. So second, another method we have, this is interrupt. So interrupt is another feature. So that is also depends on our board. So our board is actually that set um, uh, board our actually have this feature of interrupt or not. So what is this interrupt? So This is the totally different function we have. And we at the time of interrupt, so we send some signal to the processor, and at that time processor checks what interrupt is actually coming. So processor is running something in the while loop. Okay, so suppose if we have while loop and we are performing some task, but any another specific task we can done by the interrupt directly. So like the previous example, so we have, you can see we have write the separate function button interrupt. So this function is not coming inside the loop of the code. Okay, this is totally outside of the loop. But and if any interrupts comes to the CPU, so at that time, so what will CPU will hold the while loop iteration, so that will just stop the while loop iteration and call this function directly. Okay, and at that time this function will be run at so during the running of this function, so the while loop will actually stop at the previous state actually will save at some place. So what state actually that CPU got the interrupt, so that state will be saved, and after that this part will be executed. So the things is, if we want to check this LED state and based on that we decide something. So here we are passing some interrupt signal to CPU directly when we want to press, when we want to just turn on the LED or LED. At the time we are just pressing the button. So what interrupt will be passed to the CPU, and CPU will call this function at that time, and CPU will stop the another function which which it is doing actually by the inside the while loop. So in that case, so that means we are not continuously checking this LED state inside the while loop. We are just waiting for some interrupt signal. Uh, we are also not waiting, but yeah, if any interrupt comes, so at that time CPU will directly jump this function and will perform only. So in this case, so this checking the value of the address continuously inside the while loop, so it takes some it consumes some cycle actually. So that process will actually save by this interrupt process. So it will make our that embedded system efficient. Okay, it will save some cycles. So this is one topic discussed regarding this polling and interrupt things. So you can see the lecture where Professor discussed in more details. And this is another things, direct memory access. So direct memory access we have, that means memory related operations. So I'm just talking in I'm summarizing this topic. So this is totally theoretical topic. So generally everything in the computer system is handled by the CPU. So suppose if any input is coming, and then based on the task it is performing some task like this, and it is also performing some memory, if any data transmission is required, still this CPU will handle all these things. So this is the main master actually. This is the main master, primary master on the bus. So everything is connected on the bus in our say that embedded system or any computer. So like this is the main bus, and all the peripherals are connect through this bus. Memory is also connected through this. So any type of operation which is performing like data transfer, input output, any computations, all things are actually managed by the CPU. Okay, so see, this bus is actually busy. So CPU is just giving some instruction to, suppose this memory is just want to pass some data to this input output device. Okay, so that all will be handled by the CPU. So in everything, CPU is actually busy to doing all the tasks. But how we can that save some time of the CPU for this data transmission, because uh, CPU time is totally consuming data. So suppose we are sending very long data. Okay, so at that time our CPU cannot do other things because all data will be managed by that CPU from transmission. So to save some CPU time, what we can do, we can add one additional master on the bus. So that will actually perform some other task related to the data transfer. Okay. So that means now the DMA is the second master, so that will manage the data transfer things. At that time, CPU will perform other things. Okay. So Yeah, so this is the things regarding this data, the DMA things. Okay, so direct memory access. So this DMA is actually manage the memory access and it perform the data transmission, all this task without disturbing the CPU. CPU actually at that time can perform the other task. So it increase the efficiency of the embedded system and CPU perform the other task at that time. So there are some related things are discussed, and apart from that, one more thing. This is the power related, so that is discussed many times. And last topic is discussed this week. This is optimization. Uh, so how we can optimize the optimize means how we can improve the efficiency and how we can increase the time. Decrease the time to perform the task. So there are multiple ways. So first topic is algorithmic optimization. So what is the meaning of this? Choosing the most efficient algorithm for your task. So we will understand this. What is the meaning of this? Now, here one example is discussed by the prof also. So that means you can see that also. I will discuss another example. So suppose if you are performing, if you are solving some problem. Okay, so now we are not talking about any specific embedded system related thing. Simple programming. Okay, you have already done C programming and you have solved many problems. So now you found that if any we just gave you one problem. Okay, so suppose the problem is just sum all number from 1 to n. Okay, this is the one problem. Okay, 1 to n, you need to sum all the numbers. So n may be anything, so like 10, or n may be like 5. So you want to sum this number and what you want to return the result of this value. So this is one basic problem. Now there may be more than one people may come with a different solution. So there may be two different solution for this problem. So which solution is taking less time for the execution? So the our time actually efficiency is depends on that. Okay, so that means any algorithm means simple logic. Okay, so how we are solving the problem, the sequence of steps. So that logic, which logic is more fast, or which logic is taking less space. So there are two factors when we compare two logics or two algorithms. So two factors are important. So first is time, and second is space. Okay. So what is this time actually? So this is not a clock time. We generally not measure the clock time. Okay. So that's watch time. We generally measure that when we are running any algorithm, when we are running any program. So how many instructions are actually executing? Okay, because what happened, our logic or our algorithm maybe runs on different systems. Okay, so maybe if one system is very fast, so clock cycle speed is very fast, and another system have less speed. Okay, so less clock cycle frequency. So in that case, we cannot compare the time. Okay, so this time clock time is also depend on the machine that structure. So what is the input frequency, clock frequency? So because of that, this time is actually measured by the total number of steps which are executing at the running time when we are running any code. Okay, so how many instructions are executing? So that number we so that will be fixed actually on any machine. So suppose we are writing this code to solve this like this problem. So I am writing two solution for this. So what we can do, we can write is some value to 0. We can initialize like this, and then we can run a loop. So for and inside this I equal to 0 and I is less than equal to n and I plus plus. Okay, and inside this what we can do, we can simply write sum equal to sum plus I. Okay, sorry, this is not 0, we will start from 1. Yeah. So because 1 to n. Yeah, so we can write like this. Okay, and after that we will return sum. So this is the one way to solve this. We will get the correct answer by this. But what happened? what is the time for this actually? Number of operations. How the number of operations are depends on the input for this code. So here, if we are giving n equal to 10, so how many times each instruction will execute? So this first instruction, actually, this instruction will execute only one time. Okay, because our program is executing top to down manner, and we will check each instruction will execute how many times. Now the second steps for loop, this loop. Okay, so this loop is depends on the input n equal to 10. So this will be replaced by 10. Okay, now this loop, how many times this loop will run? So total 1 to 10, 10 times, and one more times. Okay, so that is for the termination, that when our condition will become false. So that means this loop will run 11 times whenever n equal to 10. And 10 times this condition will be satisfied, this one, and we will enter inside this. So 10 times this will be, okay. Now this last statement will only execute one time. So this is the, we are counting these steps, how many times these are actually running. So you can see 1, 11, 10, 1. So this is the constant. If we change any value n equal to 20, so this will be performed only one time. So this is not depends on the input. But this part actually depends on the input. Okay, if we make n equal to 100, so now this loop will run 100 times. Okay, and this will also run 100 times. So 101, 100 times. So that means this part is totally depends on the input, if and totally depends on the n size. Okay, so that means if we are giving any value n, so this loop will run n times. So we can ignore some parts. So like this is 100, this is 100 or 200. We are not calculating the exact number of steps. We are just trying out to figure out to how many, what is the relation between input and total number of steps. So this is totally this is like a constant thing. So we can write like this 1 plus 101 plus 100 plus 1. Okay, so this 2 will remain always constant, but this will become changed. So we can write like 201. Okay, or we can ignore one step, so 200. This is totally a, and what we can write 2 plus 2 into n, like this. Okay, so if we ignore this constant part, so generally we when we calculate the time for any algorithms, we ignore this constant part and we write this as a time complexity, total time. So that means if our n equal to 100, 100 times, it will take 100 number of times operations. If n equal to 1000, and so it will take 1000 number of times operation. So this code is actually totally is dependent on the input. So it is taking n number of operation when we are running this. But what happens if we are writing the another version of this code? So we are writing sum equal to, and directly we are returning that n into n plus 1 divided by 2. Okay, and return sum. Okay, so now this is the one operation for this one. So we have the different logic for to solve this problem. So now if you have n equal to 5, now you can directly calculate the sum for this problem is like 5 into 6 divided by 2. So total 15 answers. So if you get 1 plus 2 plus 3 plus 4 plus 5, you will get 40, the 10 and 50. Yeah, 50. Okay. So if you are putting this direct formula, so at that time, this will directly return the answer, but it is simply a constant number of operations. Okay, so this is a fixed operation, it will take constant time, it will also take constant time. So now you can see if you are giving any value, so like if you are giving 100, it will still, these are the two steps only will perform. Okay, here we are not using any loops or anything, so this code will perform only these two instructions to calculate the answer. Okay, so if n equal to 1000, still two number will be performed. So this execution of every instruction in general takes some time. Okay, so if our total number of operations are high, so you can see in the previous example, if we compare for the large input, okay, so n equal to per 1000, so it will take 1000 steps. Okay, but it will take only one steps, one or two steps. So we consider as a constant number. Okay, so constant, but this is a dependence as a linearly. on the input. So you can see the difference. This is performing 1,000 steps to return the answer. This is performing only 2 steps to return the answer. So definitely, this logic is more efficient when it will run. It will take very less time. Okay. So in this way, any problem can be solved with different logic, multiple logic. So that means which logic is taking less time. So that will make efficient our code. That will improve our code to run. So that will take less time to perform. So similar, we have one example like binary search. I am not sure you have listened this binary search term. So suppose if you have data, so like that, if your data is sorted, okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have written all the numbers from 1 to 11, but it may be any random number, but if data is sorted, okay, and we want to search any element in our data, okay, so this is suppose an array, and this contains any number of data, so like 100 data or any number of data. Now we want to search any data, so like suppose we want to search this 8 value is exist or not in this list or array. So how you can solve this problem? Searching in the array. Okay. So what you can do, you don't know this 8 is exists, so you have to traverse the array one by one. So you what you can do, you can start the comparison from first element. If it is matched, you will return the answer. Yeah, this is exist. Otherwise, you will move to the next element. Okay. So in this way, you can take one by one each element and you can compare the element, searching element. Okay. And so in this way, you will perform like this task. Okay. And after 7 or 8 steps, you will figure out that it is available and you will return the answer. Okay. So how many comparison you are doing in this? So you are performing linear operation. So you are comparing with each element. So maximum possibility, maximum worst case situation, your algorithm will take n times. Okay, so suppose n equal to 100 elements are there in the array. So and your searching element is coming at the last position. So in that situation, your algorithm will compare 100 times with the 100 remaining elements. Okay, then your algorithm will return the answer. So similarly, how we can improve this? So you have the same array 1, 2, 3 like this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So there is another way for searching if you have the sorted data. Okay. So that is called as a binary search. So what is the logic of that binary search is it directly compare the middle element of the sort array. Okay. It directly compare the middle element of the array and checks your searching element is greater than or smaller than. Okay. So suppose if we are looking for 3. Okay. So it will not compare with the first. It will directly check how many elements we have. Suppose if we have 10 elements, it will directly calculate the index 10 by 5 by 2, 10 by 2 by 5, and it will directly jump to the middle element 5. Okay, and will compare. So 3 is greater than or smaller than. So if 3 is smaller than, so it will not move to this side. So that means in the first step, we have removed total n by 2 elements for the searching. So total half elements are removed. Now we will only check this side. Okay. So in this case, now these are the elements we have only n by 2. Again, we will follow the same step. Okay. So now we have total 6 elements. We will check the middle element again. So now we will check the middle index again. Okay. So how many elements we have? We'll check the middle, and we will compare 3. Yeah, 3 is matched. So it will return answer in 2 steps. Okay. So you can see we are dividing the problem into half every time. Okay, so we have total n element, and each comparison we will remove half of the element. So in that case, suppose if we have total 128. Okay, so suppose we have this 128 elements initially, and we want to search any element in this 128 elements. So how it will move to the one element? Okay, so it will divide by 2, then 64. Okay, then that means we in the first step we will remove half element. So how many remaining? 64. Next step we will again remove the half element of 64. So that means we have remaining 32. Okay, next step it will remain 16, then 8, then 4, then 2, then 1. Okay. So now we are reaching till 1. Only one element is remaining. So this will be the last element to search, and we will return the answer based on this. So this is the maximum possibility for the comparison. So one step, second step, third step, fourth step, fifth, sixth, seven, eight. Okay. So that means in 8 steps we can search our element in 128 elements. Okay. So this is actually a log n value. So if you have 128, so what is this is n. So log 128. What is the value for this? So we can write log 2, and this is 2 to the power 8. Okay. Uh, 5, 32, 6. No, this is 7. Okay. Yeah. So this is 7. So 7 will come here. So 7 will become log base to 2. Now it become 1. So 7. So that means the approx 7 steps are required to find the any element. Okay, so if our elements is exist in any position in this 128, you can search in only 7 steps. So that is actually a log n time. Okay, your n may be anything. So that means you can figure out the time in log n by the log n calculation. So you can see. So yeah, please ask a query. Anyone here? Someone raised the hand. Yeah, Dhruv. Hello. Dhruv, you are not audible if you have opened the mic.
Sir, am I audible now?
Yeah, now you are audible. Yes.
Sir, I suppose the number is nine that you are going to
No, your audio is not clear to me.
one second.
Check your mic and ask again.
Sir, is it fine now?
Yeah, now better.
Sir, suppose the number was 9, that we are doing it in 7 steps. Can you show that screen? Yes, sir.
Huh.
Sir, on 5th step, it went to 8, and suppose the number was 9. So,
No.
will it then again half
This is,
it on
this
the
is-
right hand side, or it will just do it?
No. What I think you are not understanding. This is the number of elements remaining. This is not a value. Okay, this is not a value. This is a how many elements we have remaining to search. Okay, so in the above example, we can take any number of in this. I am just talking about the how many elements we have. So like I am writing 1, 2, 5, 6, 8, 10, 20, 40, 60, and 65, 100. Okay. So now how many elements we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, 11 element we have. So here I am just saying that every time we will remove half of the element in the searching. If we so here you have 11 element, you can search any element in maximum 3 or 4 times, in the 4 step any element by this method. Okay, so suppose if you are taking k is the searching element. Suppose if you are searching 60. Okay, so what you will do, you will so if we write the indexing like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so total we have this. So we will check the middle index. So that means 0 plus 10. First index plus last index divided by 2. Okay, we will take the integer value for this. So this is 5. So fifth index is this one. Okay, so we will calculate the middle index, and then we will compare the value with this. If this 60 is equal to this value, or greater than this, or less than this. Okay, so we will compare this 60 to this middle value, and based on this decision, if this is greater. Yeah, please open your mic and ask. Yeah.
Yeah, so my question is about sorting the array, because before doing the search, we need to put in the order, correct? I mean, the increasing order or maybe the decreasing order.
So
So
here I am just talking about we are assuming that we have the sorted array.
But the sorted one also will take processing time. No? I mean, in the embedded system, if it has to take time, it will take or some time it will take. Correct, processing time.
No, here I am assuming that for this problem, I am assuming that our input is already in sorted order.
Okay,
Then I am
okay,
discussing the problem. Okay.
okay. Yeah,
Okay, I'm not talking about the random order. So this binary search algorithm works only that sorted data.
yeah,
But
yeah.
yeah, we have the two way to search any elements. One is the linear search. Okay, that is actually the main search. We are comparing one by one each element, and this is called the binary search. Okay, so binary search, every time we will compare with the middle element, and then we will remove the half of the element for the searching next. Okay, so here in this case, you can see 60 is greater than. So that means the 60 will only come into this right side. No need to check on the left side. So we will remove this part to check for the remaining elements. So n minus two element, n divided by two elements are now removed in the one step. So now we have only this elements remaining. So this 10 is not matched. So we will only compare this side. Okay, this side. All this part is actually removed. Now we will check 6 plus 10. This is the index. Okay, 6 plus 10. So now 16 divided by 2, and you will get 8 index. Okay. Now then you will compare your 60 element with this 60. So now your element is matched. So in this case, if your element is matched, fine. Otherwise, again, you will take the decision. Suppose if you are searching 65 and your comparison is happening here. So that means you can remove this part. Now only two elements are remaining. Okay. So you will check for 9 plus 10 divided by 2. Then you will get a 9 value. Okay. So you will compare with this. Okay. So you can see every time we are removing half of the elements, and we will reach our searching element in log n steps in this way. Okay. So it is actually improving our searching time to n to log n. So this n is actually, this log n is very small compared to the n. If you are looking for the larger value, so suppose n equal to 1024. Okay, so what is the log n value for this is only 10. So that means if you have 1024 sorted elements, you can search any element in that sorted data in 10 steps by this binary search method. Okay, any element from this 1024 you can search. Okay, in 10 steps. Other side, if linear search will take maximum 1024 steps for some in the worst case situation. So this is very efficient approach for the searching. If your data is already sorted, then you can apply this binary search method. Okay, so now similar, you have already solved the problem to check the number is prime. Okay, that number is prime or not. So if any number is given and you want to check that number is prime or not. So like you are looking for this 37. Okay.
Sir,
Yes.
so in this, the login is of the base 2, right?
Base 2.
Okay.
So suppose same things, primary number. So what process you will perform to check the number is prime? How you check this? Anyone?
Yeah, we try to divide it with all the numbers
So
below it.
you will run a loop, okay, and you will check if this number is divisible by another number or not. That's okay. So what loop you will run actually from where to that which position you will run?
We take a square root of that number and do it. I mean, half of that, or a square root of the near number.
So which one?
Half.
Yeah, half. If anyone is taking half, okay, and yeah, some you tell that square root.
Yeah.
Yeah, that is also correct. So here in this case, which one is the efficient? So there are multiple approach. Someone maybe run a loop from for that 2 to this number, so 36. Okay, if someone is checking this number is divisible by total 2 to 36 or not. So there is a possibility that if someone is running this loop, so this loop is actually running n times. If your n equal to 1000. So that means this loop will change accordingly. So 2 2. So this value is actually n minus 1. So that means how we can improve this? We can also reduce the steps. We can run only 2 to n by 2. Okay. So this still you will get a correct answer, because if you're checking the division by this, so if any value, if you're passing 37, so it can be maximum, it can be divisible by only this 37 by 2. So like 18. Okay, so 18 is fine. After that, it cannot be divided. Okay, so 18 2 is 36. After that, if you take 19, so 19 2 is 38. So that this is the smallest multiplication you have on this side. Okay. Now, if you multiply this by 2, any value after this 18, so you will get a larger number of this. So that means after n by 2, there is no need to check for y multiplication, because it will not divide definitely. So this is the one possibility anyone can think. So other is 2 to the 2 to square root of n. Okay. So any number, if you are writing like 1 into 2, okay, and you have this situation. So like 1, not 1 into, sorry, 2 into 2, 2 into 3, and like this. So square root of n. Suppose if you are taking 16, okay, so if you are just checking that 2 into 8 we are getting, okay, 16, and if we are increasing this side, it will be decreased actually. Okay, so what value we can take? So we can take 4 into 4 maximum. So just yes, I got this. Okay, so what I was thinking that, yeah, square root is also enough, because if you are multiplying this 4 into 4, so okay, so this is the square root value of this. Suppose this is n16 and this is the square root value. So you can get the answer like in between this 4 into 1, 4 into 2, 4 into 3, and 4 into 4. After that, this is the maximum range you have. Okay.
Sir, your board is not visible.
Hello.
Yes, sir.
Sir, your board is not visible. It's showing Google Meet.
Am I audible?
Yes, sir.
Okay, okay. Yeah. So to check any number is prime or not, so this is only enough sequence to check if your number is prime or not. Okay. So what you can do, you can just divide the value by this n by 2. Okay. So n by 3 like this. So if your number is divisible by any value of this range, 2 to square root of n, so that means that is not prime. Otherwise, your number is prime. Okay, so yeah, this is the possibility. That is the enough actually to check till 2 to square root of n. No need to run a loop from 2 to n by 2 or 2 to n completely. So this n and square root of n. Here you can see this is the difference between. Okay, so like if you're giving 64, so what is the square root of this value is 8. So 8 step and 64 steps. So there's the much difference. Okay, so in this way you can achieve this value 64 maximum in 8 into 8. So if you divide this 8 into 8, you can achieve. You cannot achieve this value like 8 into 9. After that, it will be actually increase up. Okay, so no need to check from out of this range, square root of this range. So that means this problem can be finished in square root of n steps. So in this way, many problems are there where efficient solution can be written. So the same things is discussed in the lecture, so that you can improve the efficiency by improve the algorithms actually. Okay, so this is algorithm optimization. So the professor have discussed the sorting algorithm. So I'm not sure you are aware of the sorting algorithms because it is not discussed in your C programming course. So there are multiple sorting algorithms we have. This algorithm means this contains a different logic to solve. Okay, so many popular is this standard algorithm like bubble sort, insertion sort, quick sort, merge sort. Okay, so all have different approach to sort the elements. Now which one is the better actually, which takes large time, which takes less time, so that is depends on the algorithms here. So this bubble sort and insertion sort actually costly algorithms, it takes large time compared to the quick sort and merge sort, that takes actually less time. So the time, if we talk about the relationship, so this bubble sort or insertion sort takes n square time. Okay, order of n square. So n square means if we are giving n value, so our total number of operation will perform in the ratio of n square. Okay, but if quick sort, if we are giving n input, so our total number of operation will be performed in n log n steps. So this is much better. So if you are giving like 1000 input, so that means this algorithm will take 1000 into 1000. Okay, but this side it will take only 1000 into 10 approx. So it is much better. So in this case, any algorithm you can improve your logic, and you can reduce the steps. So that will also improve the efficiency or improve the time of your system. So your application will perform quickly run. Okay, so it will take less time to computation. So that will make improve the efficiency of the code. So this is one discussed algorithmic optimization. Okay, and memory optimization is also important. So like this is also very important topic regarding this embedded system optimization. So because we have the limited memory, RAM and flash, we have the limited in the embedded system. We doesn't have like the general system. So in that case, suppose you can see this example. Suppose we want to store there's 100 elements. Okay, so sensor data, uh, and that will contain the 100 value. So what we can do, instead of writing, so if we are getting some specific data like 1 0 or some specific single value, so that can be handled in, so this int take actually 32-bit. Okay, 32-bit if we are declaring our this sense data array, and each element is taking 32 bit or 4 byte. Okay, so 100 into 4, 400 bytes is required. But if our each location of the array is storing only that small value, okay, small value. So what we can do, instead of declaring this array with integer, what we can do, we can declare this with size uint 8. Okay, so this is actually equivalent to the char size. Okay, so char size. So what is the size of char is 1 byte only. So this is also taking 8 bits. Okay, so 8 bits means 1 byte. So that means if our value is small to store in each location, so we can decide our data structure, and we can reduce the size of our each element. Okay, so here our each element is taking only 1 byte to store the data. Okay, so we can declare our array like this, so it will reduce the time. So it will, for 100 element, it will take over 100 bytes. And the above example, that above one is taking 400 bytes. So in this way you can reduce the space in memory. Okay, you can reduce the space in memory, and that will improve the efficiency of your that system. Okay, so you can minimize your that data structure space. You can decide that what is the minimum requirement you have. Based on that, you can declare your data type or data structure, so that will improve the efficiency. So like this you can improve CPU optimizations. So how you can save the time of CPU. So that CPU optimization, there is a one example here. So loop unrolling. Okay, loop unrolling means you can see this example. Here this loop is running 0 to 100 times. Okay, and every time we are running this step, process data I. So in the each iteration, so you know that in the for loop there are multiple things. So this first actually is the expression only execute one time. Okay, this step is actually execute in the every iteration. So that means your I will be incremented one times, and that this condition will be checked. Then you will enter again into the loop, and then you will execute. So every time this one step, second, third, so these three steps are executing for the 100. So total 300 times steps will be performed for this. So how you can make uh, this loop better? So you know that your iteration is running for continuously index. Okay, so data I. So next time this will become data 0, then data 1, data 2. You know the index. So index is running based on the I value 0 to 100. So what you can do, you can just reduce the number of loops. Okay, you can reduce the number of loops, and inside the loop body just perform the above task 4 times. So like this first call with I, the second I plus 1, I plus 2, I plus 3. Okay, so that means in the each steps you are performing 4 this steps, process data with 4 index. So I plus 1, I plus 2, I plus 3. So that means this 4 steps will perform, and now then it will move to this increment. So we will directly increment by 4, because in for single value of I we are utilizing the 4 steps. So I plus 1, I plus 2, I plus 3. Then we will directly jump to the next 4 value by adding the 4 step value, okay, in the I. So in this case, this loop, this increment operation, this conditional checking is now reduced. So how many times this loop will iterate? Only 25 times. So we are incrementing our value by 4 every time. So that means it will run only 25 iterations. Okay. So 25 times this condition will be checked. Okay. So this will be checked. Okay. So 25 and 25, total 50. So 50 times only this two operation will be performed. After that, this 4. Okay. So 25 into 4, 100 times. So 100 times this will be steps. So this is the 4 step into 25. So total 150 steps are performing in this situation. Okay, so you can see in the previous case 300 steps. So this your CPU is actually busy for this 300 steps by this process. Okay, so it will take more cycle. But in this way, we are reducing the some steps by this. We are writing this loop in this way. So our total 150 times only this steps will be performed. So in this way we can optimize the CPU, so we can do some improvement steps. So this is the main topics, that IO optimizations. So we have to reduce the overhead of the input output operation using DMA, or that is, so some operation can be directly handled by the DMA. Some, if you are getting some data related operations, so that will be managed by DMA. So power optimizations, so how you can reduce the power, so you can, so that you're using the sleep mode. Okay, so if any task is not performing, so your CPU can move to the sleep modes, reducing clock speed, turning off unused peripherals. If your peripherals are not actually used, so you can turn off the clock for that. So that will reduce the power of the your system. So in that way, there are the many way to optimization in for the this embedded system. And code size is also one there. So that, because you know that your that memory, that fixed non-volatile memory you have for the firmware, so that is also limited. Okay, so you cannot upload the very high size code. Okay, so that is also limited. So just try to write your code with less size. Okay, so just try to write less number of instructions, so that will take less memory. So you can reduce the size also of your code, so that also takes some memory in the firmware memory. Okay, so in this, these are the topics where you can perform the optimizations in the embedded system. So these are the topic which is discussed in the Beak 10, so related this things. And yeah, this is the one thing. Now, the another things actually, as I mentioned that in my previous session, so that regarding the driver development. So I'll okay, I'll discuss that thing also. So what is this driver development? Okay, so this is the Big Ten content. Now you can just watch the video. You will get more clarity in this. Uh, Otherwise, now moves to the next part of the today's session. That is actually driver development. Okay, so
Sir,
yes.
I have one doubt on the initial example which we discussed
Mm-hmm. Yeah, which
about
one?
the code of.
Yeah, which one?
Yeah, yes, sir. This calculating this sum.
Mm-hmm. Yeah. What's
So
your doubt?
using this formula would be the best way, right, sir? Both in time and space optimization.
Which formula?
N into n plus 1 by 2.
No, this formula is for one specific problem. Okay, this is not for the all problem. This is not a formula for time. Here the problem was we want to get the
But I
result
mean,
of, yeah, sum of all number from 1 to n.
yeah,
So
yes, sir.
one way
So
is actually to get the solution by the loop. Okay, another way is to calculate the sum by the formula. You can directly use
yeah,
this
yes, sir.
formula.
So this take less time to do the
Yeah,
work,
yeah,
right?
definitely it is only single steps. So this is simple calculation, arithmetic calculation. So CPU will perform in only constant time, fixed one time. Okay, so
And
if
the
you
memory consumes
so no, actually, this is
also.
you are passing to the CPU this n value. That CPU will perform these operations so that it will increment the another. So it will actually take another register. So by incrementing this value, after that it will perform multiplication. Then after that it will perform division. So only to perform this calculation, these steps are required by the CPU. Okay, so it is not depends on the that your number of steps are not depends on the n value here. Okay, so
Yes,
that this is a single step. It will perform. It will take fixed time for any value of n. Okay,
yes, sir.
so it is not iterating in the previous version of the solution. We are running a loop. So here these steps are depends on the uh, our input n value. So if we are passing n equal to 100, so this loop will 100 times. So that means this step will perform 100 times. Okay,
Yeah,
so
yes.
it will definitely take more time.
And sir, using a for loop and using a recursion function, will it be any different or same?
No,
Because
yeah,
both.
recursion is more costly.
Oh, okay.
Okay, recursion is
But,
more costly compared to the simple iteration. So what happen actually when if you're writing a recursive function, suppose a factorial. Okay, so if you're writing a factorial like so factorial 5, and inside this you have written the base case. So if that this value suppose this is n, so if n is equal to 1, then you are returning directly like 1. Okay, otherwise you are returning recursive value. Okay, so fact uh, sorry, not
minus
this n into fact n minus 1 like this. Okay, so this is the solution, recursive solution for factorial. Okay, so
yes,
what happened actually when this function is called, suppose n equal to, if you passed 5, so that first time this you will enter inside this, and here this expression, so this will be execute like this. So here, and this is a now new call. So your this is the new call, and your same function will start again, new copy. Okay, of
yes,
this copy it will start again for fact 4. Okay, same function will start execution of again. But what happened, you are jumping from this position, that means some operation are pending in the previous state. So 5
mm,
into, and you called from this position, and still you have not received the return value for this position. So this operation is actually still pending till. Okay, so that means this state actually will be saved in our some memory. So that means this operation will be performed after the returning value from this function. Okay, till then this state will be saved some memory. So that will take some so that means it will saved at some place So that in this way, this call will be happen multiple times. After that, you will get a return solution from each function, and after that, you will return a solution from this position. Then it will perform back. So every time when you are calling again, so the previous state is actually saved at some place, and your when your function is complete, that means you need to jump back to that state. So this time this is overhead actually. This is overhead for the computation. So you are storing your previous state at some position, and you are jumping to the next call, and then again next call. Each time you are saving the current state, and after that
Okay.
you will receive a return value, and then you will just jump to the save state, and you will return back, will perform the computation, and then like this. Okay, so here overhead is actually increased. This saving the state is actually, it is the overhead actually for the computation. So if you have the solution, like if you are writing a solution, and if your solution can also be also be solved using the iteration, simple iteration, while loop, for loop, so always prefer
Yeah. Yes.
the loop version.
Looks. Yeah. Yes.
So that is also a one optimization way.
Okay. Yes.
Okay.
Yes.
Yeah. So yeah, regarding as I wanted to discuss this driver development. So last time we have discussed some code. So that driver development. Okay. So what are the things for the driver development? So we have some layer actually when we are working with the any embedded system. So there is one that application. Okay. So this is first a user application when we develop the application. So this is the application layer. After that we have one next layer that is called as a driver layer. Okay. So here this is the driver layer, and after that we have MCU. Okay, so MCU, so that contain all the GPIO, so that GPIO, and other peripherals, so that contain all the peripherals things, so like SPI, this is we have I2C, UART, I2C, UART, so all these are actually
And
peripherals.
HL
Hmm?
will be
Which
below
one?
the driver or above the driver? HL.
So HAL, this is the similar things. Okay, so HAL, this the same which we are talking about. Okay,
Okay.
so
Okay.
yeah, that is actually we are talking about how that HAL actually developed. Hmm. So here actually this layer come in between this application where we are designing some application on the FCMCU, and this is the physical hardware. In between we have some layer, so that will actually reduce our task to interact with the directly to the hardware, and we can perform the operation with the help of this driver layer, and that driver layer provide the API. That means that will provide some direct function, already created the function, we just need to pass the value into the function, and it will return a that required value. Okay, so this driver layer actually perform the intermediate task, and it actually interact with the actual hardware, but we need to interact with only this driver layer. So in this, what are the things actually in this driver layer? So this driver layer contain a one header file and source file. So there are two types of the files actually this driver layer contains: .h file and .c file. Okay, so this is a header file, this contain the definitions things, okay, definitions, macros, and this is the source file that contain the functionality type. Okay, uh, for the related to the peripherals or these things. And inside this driver file, one specific file we generally use for the MCU related. Okay, so MCU is specific because we can use different MCU board. So one header file. Okay, so this is H file. One header file we created for MCU specific. Okay, so MCU specific dot H. So that contain all the information like what are the memory base address, what are the peripheral base address for that. Okay, what are the RCC, that clock control base address. So all the base address, memory address, all that contains by this header file MCU.h. Okay. Apart from that, that this contain the file for each specific peripheral. Okay, so that means it contain the file of GPIO. So this is one type of peripheral. So GPIO.h and GPIO.c. So these are the two files. Okay, so this is the peripheral specific driver file. Okay, so inside this main complete driver. So this driver layer actually contains these type of file, one specific MCU header file, and apart from that, each peripheral specific header and source file. Okay, so like this SPIO, SPI dot h and SPI dot c. Okay, so same for UART. All how many peripherals we have, so that actually that files will be created for each separately. Okay, so this is the structure of the project where the driver is actually developed. So what are the steps to perform if you want to perform this driver development? So that means first is this MCU specific header file is required. After that, second step is just create this peripheral specific driver header and source file like this. After that, you can create this application. So this is the first step, this is second step, this is third step. Okay, so create all this file, and then you can directly interact with this driver files and you can perform your task. So I have created one project for this. I'll also tell you the starting things, how you can start. Okay, so I have created this one, but it could not complete actually. Something is pending. Okay, but I'll give you the idea. So how you can start creation of this. So this is the QID. I'm working on this STM32 board, and I have this Nucleo G4. Yeah, please ask if anyone has. Yeah, Muthu.
Sir,
Mm-hmm. Yeah, what you are asking?
so sir, how these header files can be compared to the stdio.h in C language?
This is very similar. Okay, so that header file is also the one file which is created by the that program that manufacturer, those who have developed the language. So that stdio.h, this is the standard input output which is created by the those who have developed the language. Okay, similar way you can also create your header file. So this is also this is very similar, the same header thing. Okay, so header file is just that contain the definitions or functions, all these things. So you can directly call that function and perform the task. So same things, you math.h you include in your code. So that library is created by someone and it is approved by the language and you can use that. So same things we are trying to do. Here we will create this header file for this our board, actually specific for our board. Okay, so you
And
can
the
also include that. Hmm.
OS will be not coming on top of driver. I mean,
OS. No, we are working on the OS. So if we are, so which OS you are talking about? Here we are
no, I
not
mean,
using OS actually.
in this topology, OS won't be there. Directly application we can build using a driver.
No, what you are talking about embedded system, or you are talking about this IDE related things?
No, I'm talking about the architecture which you just showed us, that there is, I mean, the first level is hardware detail, then driver is there, that is,
So that things OS. What is OS actually? We are interacting with some applications. So like we have some IDE. Okay,
yeah.
so this IDE is running on some OS. That OS is actually from our this computer, not for the embedded system.
Okay.
So
So
that
in this
is
case,
actually, yeah, that is actually not using any operating system. So that our is embedded system. Here we are
okay.
working some on the some IDE and we are creating the code that we will upload on the our MCU, that it will run actually by the CPU directly. So in the embedded system, OS is not there,
Yeah.
but here in our computer, OS is actually running this IDE. Okay, so
So
this is just the interface.
So whenever we are loading the application code, we have to load complete driver code also every
Yes,
time,
yes,
or
yes, yes. Yeah, correct. It will be.
okay,
It will also be load. Actually, the all related file will be load.
loaded again. Okay.
Hmm.
I was thinking that okay, driver once we load it, then it will load only
No,
application
if
code.
any definition is defined inside the driver, and you are calling that function, and so that means that related code should also be upload in the
Okay.
controller. Okay.
Yeah.
So when you run any C program also, so C program is not actually what you are writing in the compiler. So that part is not only run. Okay, so after that, if you are using this scanf, okay, scanf, printf operation, where you have included this header file stdio.h. So when you run your program, so that actually file is converted into the assembly language, then machine level language. So in between this process, your all code related to this, your printf, which is defined inside the standard library, that actually also included in your code. Okay, so all related call file or function which you have included in your code, all will be included in your file, and that will be processed to the execution.
Okay, understand.
Okay. So here I'll tell you how we can create a driver file. So one I have created, but it could not complete. It is still pending. So but it is closer to complete actually. So I'll try to from the starting point. Okay, so how we can start. So we will start from this file. Okay. So yeah, currently I'm using this STM and my board is that STM32 Nucleo G4 board. Okay, so I am selecting this new, okay, as a new project. Inside this new project, I will select this STM32. This, okay, so this is a new project I'm opening. Okay, so now it is asking for the board. It is asking for the board, and board selector. I'll select my board. So Nucleo G4. So G4. That this one, okay, and now this board is coming, so I'll select this board and next. So this is very similar to your project creation. So now this time I'll give some name to our project. So now we are creating driver, so I'm giving the name like this STM 32, and my model is G4. Okay, G4, and uh, G47 something, or we can skip here. So G4, after that we can write like XX. Okay, and after that we can mention, so this is driver, so driver. So I'm giving the project name. Okay, so what project? So this is driver, and I've already created previously, so this test, I'll give another name for this, so test 2. So now we will select this empty. Okay, so we will start from the scratch. So after that we will click on this finish.
Sir,
Yes.
why only C and C++ languages are there?
uh, when we are opening that, okay, so this actually uh, support this language only. Otherwise the you have another board also that support this python, that code, but this STM32 supports only this.
Okay, yes, sir.
Okay, so every it is depends on the board actually, so which language you can write the code. So some board are there Raspberry Pi, so that support python language. Okay,
Yeah,
so
yes, sir.
now I have opened this new project, so test 2, you can see. So these file are the structure I am getting. So you can see inside the source we have the main.c. Okay, this is the empty now. Okay, nothing is there. So this is actually a application layer. Okay, this part is actually a application layer where this src actually contain this main.c, and inside this main.c we will write actually a application code, what we want to do. Okay, so this is the application layer, but how we can include more file in this project, so that we will create a one more folder in this. So how we can create a folder? So click on the project and just new and folder. Okay, so folders, and we will give the name of folder like drivers or simple driver. Okay, so you can give any name like this. So driver. So now one new folder is created, but it is not included in your project itself. Okay, when you will build your project, it will not actually include it. So this some indication is also there. You can see. So how we can include this folder in our project, so that will also be build actually when we will build this project. So we can click on this and we can move to the properties, and after that inside this uh, okay, so yeah, this one. When we open this property, you can see this tick mark is there. Okay, so exclude resource from build. So this is actually exclude now. So what we will do, we will just uncheck this, and after that and apply and close. So now this is included. This driver folder is included in our project. Now what we will do, we will create a driver. So we will create a another two folder inside this. So that is actually one folder is for header, another folder is for source. So for header folder, we will give this name inc. So that in general, this inc folder contain the header file. So finish, and another folder for source file. So new, and then folder and src source. Okay, now these two folder I have created. Okay, so after that what we will do, we will create a first header file inside this inc. So this header file is basically to basically for the that uh, that MCU specific header file. Okay, so MCU specific header file. So we will create a header file. So new, inside this we will create this header file. Okay, header file, and where we will give the name like this stm32 g4. Okay, g4, and like xx. So xx means some model name. So after that driver dot h.
Sir,
Yes.
should we include these two also, the build like driver?
No, this folder is complete. Yeah, this
Okay,
folder is
okay,
completely included now. Okay, so we are
okay,
creating the another folder inside this, so that will also be included.
okay. And sir,
Okay,
what are those includes and startup folders?
so that are actually application related things, so application layer related things, so that is created by default. So we will that contain the files related to the applications code. This is not a
Okay,
driver code actually. Okay, so this we are creating one specific header file for MCU related. Okay, so you can write like this. So this is a specific 32 g4, so you can click on the finish. So this .h file. Okay, now you can see we are getting this small by default code, so you can write your code in between this, and this is one header file. Okay, this is this is there, nothing is written for a specific task. This is by default some code, so you can ignore this. How we can check this is included in our code or not? So we can click on this main.c, and inside this main.c, what we can do, we can check this is included in our code or not. So just remove this part, and inside this just test has include. Okay, if your library is not that standard, so in that case you can include this in like with the double quote actually, not with this arrow. Okay, greater than or less than symbol. So what was the name of our header file of this? stm32 and g4 xx underscore driver dot h. Okay, so I'm including this. Let's run this code and check it is our that is it is building or not. So build project, you can see we are getting error. So actually we have in called this, we have included this header file from our main.c, but our build system actually doesn't know that where is this file located. Okay, so where this file is located, this header file. So that path is actually not uh, defined. So we have to set this path also for this. So what we will do, how we can set the path. So we will click on the right click on this, and again properties, and this time we will click on this C++ build, inside the setting, and inside this MCU GCC compiler, and this is the one include path. Okay, so when we click on this, you will get a this plus sign here. Okay, and inside this plus sign, when you click on this, so you have one option workspace. So now inside this workspace, select your project here, and inside this you have a driver folder, and inside this driver folder you have this inc. Okay, click on this and then okay. Okay, so now you got the path, and click on the okay, and then apply. Okay, just click on this rebuild index and apply and close. Okay, now we have included the path, and again build this. Now you can see it is running fine. Okay, now path is set. Now you can access this header file in your main.c, and that will be accessible. Okay, so this is the primary setup for the file creation, and now we are creating one header file. Okay, so one header file which will contain the all microprocessor, that controller related information, so all the macros, all base address, all these things. So this is now the initial steps you need to do when you want to start the header file creation. So inside this driver folder, all header file will be created inside this inc. So one is this specific MCU specific. After that, we will create that GPIO, or that peripheral specific. Okay, and source code will be included inside this SRC folder, driver related. Okay, so this is the first step. Now I have already done the code. It will take too much time actually to write again, because we need the reference manual, all these things for this. So I have created one files here. So this is very similar. You can see we have the same type of files. Now we have one folder drivers, and this contain this inc and src. Okay, inc contain this specific file stm32g4xs. So this is this MCU specific. Okay, now when I click on this, so this first file is open. Now I'm removing the current file, so that we have just created now. Okay. So this is the header specific, that MCU specific file. So what type of data we actually contain inside this, and how we write the code. Okay, so this contain most of the things macros. Okay, that's C macros, which we have learned in the C programming. So now you can see what type of information. So this is the by default code we already got, but after that, in between, you can see. So the information we generally contain like this: define the base address of memories. Okay, so what type of memories we have in the MCU, so that you can define the base address for that memory, so where that memory is actually started. So how you get this information? So generally there are two important memory we have. One is flash memory, and another is RAM memory. So RAM memory is basically volatile memory, and flash memory is actually non-volatile memory. So that contains the code actually that will not delete if your power is off from your MCU. So what are the starting base address for these? You can define. So this is the macros only. So we are giving some label. Okay, we are defining this label for this address. Okay, here what is the meaning of this U? Actually, this is defining that this address value is actually this is not an integer. So this is unsigned, actually unsigned value. Okay, because address cannot be a signed. Okay, so this is a unsigned value. So because we can define this like as a U. If you are writing U, so that it means this value is actually unsigned value. So we are giving label, and that will contain this value. Okay, this is the base address. So how we got this information? So we have this manual. This one. Okay, so inside this manual you have this first specific, this memory organization. You can go on to this, and inside this memory organization, you can see this table we have. Okay, and inside this table you can see you have given this information. So this part, yeah, this part. Okay, yeah, so you can see the address is started from 000, but this part is actually related to the system memory that contain the code. Okay, uh, and SRAM is actually started from this address 200 SRAM 1. Okay, we have more type of memory, you can also define that, but generally we use this SRAM 1 and flash memory. So that flash memory is actually started from here, so that 800 address. So you can see this information in this, not this, reserve or some memory organization. We have more data, so that flash memory you can search in this. You will get more details. So like this is SRAM and that flash memory operation. So you can see this information, and some place you will find out this. So you can see, yeah, this range you can see, this is flash memory, this range. Okay, and this memory is actually SRAM1. So you can get this information for SRAM1, where it is actually very common in most of the MCU of STM. Okay, so this address is for SRAM and this is for flash memory. So you can define this address, and after this that we have more information required, so we will come to this. Okay, let's move to this. So we have defined this base address on this, and we have given name. Okay, so flash base ADDR. Okay, address. So we can give this type of name which we can recall easily. Okay, so this is just a naming convention which actually commonly used in the driver files. Okay, and it actually easily understandable what is actually representing. And generally we represent this macros in the capital letter. So if any time we use this, so it is actually clearly we will understand that this is a macros. Okay, after that memory we will define the base address for peripherals bus. Okay, so we have different types of bus in our microcontroller. So generally four type of bus are there. So that is one APP1, APV2, AHV1, AHV2, and all peripherals are connected to these bus. Okay, APP. So generally this AHV1, AHV2, this AHV actually are the faster bus, and these APV are the slower bus, and our peripherals are connected to these bus. So we should know what are the base address for each bus domain. Okay, so that we can define. So you can see the same reference manual, and you can see this side, this bus name is given. Okay, so APV1, and where from it is starting you can see. So this APV1 is starting from this address 40001. Okay, and after that APV1 and then APV2 will come. So this is starting from this address. Okay, this one. And AHV1 address is starting from this position index. AHV2 is starting from this address. Okay, so all address we have defined inside this. You can see this is the starting address of the peripheral base. So all this actually are come from this peripheral. So then this is the second address we have seen. This is the third, AHV1, AHV2 base address we have defined. After that RCC. Okay, so this RCC is also important because we need to enable clock for the peripherals. So what are the RCC base address? So this is clock control. Okay, so where is RCC comes? So RCC you can see inside this, you can see all the peripherals name. So inside this peripherals you can see this RCC. Okay, this one. So this is connected to AHV1, and starting address of this is, okay, so you can define this RCC address here. Okay, now this is done. After that each GPIO now define peripheral base address of AHV2 bus. Now I have mentioned only this one example. You can define the peripherals of each bus which are actually there. Okay, so I have just mentioned this as an example. So how we can define the peripheral address? So here this GPIO, all GPIO actually address is defined. GPIO A, GPIO B, so like GPIO G we have. So in this document, you can see this GPIO are there, like here. Okay, so this you can see this to this one GPIO. This is connected to AHV2. So that means we will start from this AHV2 base address, and after that we will add this value. So 0400, then 0800. So by this way we will add the value only, and we will get the each peripheral GPIO base address. So that is defined here, you can see. So we are simply taking this base address, HB2 base address, and we are adding that value. Okay. So in this way, after that, in the base address, we are adding this value. So we are getting the GPIO B base address. So like this, we are getting each base address. Okay. So in this way, we will define the base address of each peripheral. So now this is the GPIO only. So after that, uh, okay. So now what? Yes.
Sir,
Yes, yes.
in the address, why everything is ending with U most of the thing?
So U is actually representing that this value is unsigned.
Okay.
Okay. If
Yeah.
we are not mentioning U, so it will represent as a signed value, but address cannot be assigned.
Yeah, yes, sir.
Okay, so this represents unsigned.
Yes, sir.
Huh.
And sir, what is the full form of AHB and APB?
Yeah, you can see this information on the port, that board specific. So what are these?
Okay.
Okay. Or in the reference manual you can see. But yeah, I know that this AHV1 bus is actually faster bus.
Oh,
Okay,
okay.
but APV bus is actually slower.
Yeah, sir.
Okay, so just check the reference manual and
Yeah,
you will
sure,
get
sure.
that name. Okay.
Yeah, yes. And sir, what is this? What is SRAM and where we use it?
So
It
SRAM
is
is basically it
static RAM, right,
required,
sir?
not static. This contain the data at the time of computations. So that this is actually volatile memory. So when our CPU is performing some tasks, so any data is required, so that data will store during the computation. It will store in the RAM.
Yeah.
Okay,
So how
but
is it different from normal RAM, sir?
so no, this is a RAM actually. This is not a different difference. But here actually we have another type memory, flash memory. That is
Okay.
non-volatile. That contain our code, which we have
Yes.
generally upload in the MCU.
Okay.
Okay, so that code will not be removed if you remove the power of your MCU.
Yes.
Okay, so that
Yeah.
code will execute. That code will be come to the RAM and then it will be execute.
Yeah. Yes.
Okay, but that flash memory you can rewrite. So that option MCU provide. You can upload the another code in the same memory.
Yes, sir.
That is not actually like as a ROM.
Yes, sir.
Okay, you can update that.
Yes.
Uh-huh. So yeah, this is the one part. After that, now we have defined this GPIO, all the base address. After that, you know that we have the registers for each peripherals. We have done this many problems based on this register level, and each peripherals have their registers. Okay, so like GPIO, you have seen that in the document if you see. So if I open the any peripherals, so like GPIO, this is RCC. So RCC you can also see it also contain their registers. Okay, and same way we have GPIO, general purpose registers. Okay, so this GPIO registers you can see. So now from GPIO registers, just checking. Okay, 1 second. GPIO and registers. Hmm. So you can see this is the GPIO register. So if this is the peripheral, after that each peripherals have their registers to set mode or set the input data, read the input data, output data. So according to the functionality, each peripherals have their registers. Okay, so here we have I think nine registers for this GPIO. Okay, so that is one mode register, port mode register, which mode actually we want to use, input mode, output mode, Okay, like then another register we have output type. Okay, next register we have output is speed register. That this is the pull up pull down registers for GPIO. So all these are the registers for the GPIO. So how we can define this GPIO in our MCU specific header file? So there is one efficient way is to create a structure actually. Okay, so we can create a structure, and where we can define this mode as a commonly. Okay, so this you can see this is defined all the modes for the GPIO. Okay, so this part actually have contained the peripheral registers definition structure. So this type structure contain the all mode. Okay, so all value actually have the what how, so this is 32-bit value. So each registers have 32-bit size. So because of that we are taking this unint 32t, and we are using this volatile to just save for the optimization process, because sometimes this our that MCU performs the optimization if our data is not defined by this volatile thing. So maybe some case it may be skipped. Okay, it may be skipped. uh, it may be optimized actually. So what will happen, some operation will be skipped to just make the code optimizations. Okay, so in that case, we want that if any operation is reading using this mode value and using these registers, and these registers actually commonly update. Okay, so the value of the registers is update at the time to time. So that's this registered part should not be skipped actually by the compiler for the optimizations. Okay, so if we have defined this variable as a volatile, so that will not be optimized by the compiler. Okay, so that part of the code will not be skipped for the optimization. So that this will definitely be execute. So because of that we define this volatile. Not all registers require this volatile things, but some registers require this. Okay, but still for the safer side we will declare all this mode registers as a volatile type. So this is the structure. You can see now the memory sequence actually why we declare this in the structure way. And we will also follow the sequence of registers, because how we will get the address for this, because each register also have the address. So you can see what is the address value, how we calculate the register address value. So what is the GPIO base address we have, after that we add this offset value. Okay, so port mode registers we will add this offset value. Next register we will add this 04 offset value. Okay, so this is every time 4 byte actually is now increased. Okay, so 4 byte means 32 bits we are moving to the next registers. Okay, now you can see 08. So in this way we are moving to the next address. So we will add 4 byte and we will move to the next address from the base address. So when we are creating this structure here, so it is also performing the same thing. We have declared this as a 32 bits, and we are creating our structure. So that first address will consider as a 00 offset. Then next will be considered as a 04 address. So that 32 bit will be consumed by this. So next 32 bit will be consumed by this. So that means it will move to the next address after 32 bits, then next 32 bits. So it will actually these are the variables declared inside the structure. So it will take the memory consecutively after the gap of 4 byte. So we have declared this structure. Now for registers we can directly fetch this as a option. Okay, so we will declare our variable of this type of structure. So like this is the type, this is the structure name GPIO register definition. Okay, so this underscore t just for the data type. Okay, so this is the GPIO register definition we have defined inside this structure. Similarly, another this structure we have defined for RCC. Okay, so clock, and clock contain many number of registers. You can see this number of registers. So which one will be useful? So we need to enable our GPIO. That clock we have to enable the clock for our GPIO, and our all GPIO are connected to this AHV2 bus. So you can see there is one register inside the RCV. We have AHV2 in enable. Okay, so AHV2 ENR. Okay, this. Okay, so inside the RCC we have these number of registers. So we have defined all inside the structure for the RCC. So this naming we are defining. Later we will use this. Now you can see peripheral definition. Okay, we are defining the peripheral. So each peripheral GPIO A. Okay, so now what is the, now you can see what data type we are taking here. Okay, so we are taking this GPIO register definition TST. So we are making this as a pointer. So GPIO we are making as a pointer, and base address of this is GPIO base address. And what is the what typecasting we are using here? That this is structure typecasting, this one. So that means we can use, after getting the base address, we can simply, like if we are declaring any variable based on this, so GPIO A, then we can use the field like GPIO A, then this is a pointer, so we will write the condition like this. So GPIO A, GPIO A, and then arrow. Okay, so how we can access the member of our structure like this, okay, from the pointer. So that mode R, so we can write like this. So if we are writing like this GPIO A dash mode R, so that will reach at this first register. Okay, if you are writing this OT type R, so you will get a second register of the GPIO A port. Okay, GPIO A port, and for that you will get a second register. Okay, you can fetch the value of second register by adding the this value 44 byte value. So in this way, we are defining all the peripheral definitions. So GPIO is the now pointer, and that contain the these number of registers. Okay, you can fetch through the that arrow symbol. Okay, because of that we have done this typecasting. So address is actually will behave work like this. Okay, so same things for RCC. We have defined this RCC. Now the RCC base address, and this how we can access all the registers. Because of that we have used the typecasting of this structure RCC. So we can access all the register by the RCC arrow and that register name by this. And some common required function we can directly perform here. So like we want to enable our clock. Okay, so we want to enable the clock for any specific peripheral that like GPIO A, GPIO B. So how we can do directly? So we will call only this function, and when we are calling this function, this operation will be performed. Okay, so RCC AHB. Okay, so RCC is the that peripheral. Inside this is the register AHV1. Okay, and AHV1 ENR. Okay, RCC AHV1. Okay, huh. Okay, so this GPIO. Okay, I think this is wrong because our GPIO is now connected to AHV2. AHV2. So yeah, this is the wrong. We have to enable the 2, not this one.
Sir,
Yes.
is there any way by which we prevent the compiler from optimizing the whole program which we wrote, like we mentioning the volatile?
So there are some way to that prevent actually. There are some setting you can some ways you can define your variable like using this volatile things. Okay, so if you define all the variable volatile, so that will be actually not optimized. So otherwise you can stop the optimization process by some setting. That setting I have checked, but right now I'm not sure where that setting will be. Okay.
Yeah, I see.
Otherwise, some features are there you can that prevent from the optimizations.
Yeah, I see.
Yeah, that maybe I'll discuss in the next time. Okay.
Yeah, I see. Sure.
So now you can see we can directly enable our clock by this name. So we just call this function. So from our function GPIOA, that this function, that peripheral clock enable. Okay. So when we will write this function, so this part will execute actually. Okay. Now GPIO, that RCC, this registers we require, and in this registers we need to set zero, that set that first bit. Okay, so that first bit to 1. Okay, and in this case we need to set the second bit, then third bit, like this. So we will set our bit to enable our clock. So if you remember this RCC registers, so that if you move to the RCC here, the documentation, so RCT clock. So you can see this AHV1, or we can directly jump. So AHV2, actually AHV2 enable. Uh, yeah, this one. AHPV1, AHPV1, and AHV2. Yeah, this one. Okay. So AHV2. So you can see these are the GPIO enable bits required. Okay, so AHV2 enable offset, we need to set this bit. Okay, so GPIOA, we need to set this first bit as a 1. Okay, so in this way we can set reset. So this number of fields 0, 1, 2, 3. Because of that, we written this information in our header file. Okay, so if we want to enable GPIO A, we have set this 0th bit. Okay, then first bit, like this, and we are performing OR operation. So we have written this, and if we require to enable, we will directly call from this. Some generic macros are required. So like we want to enable something, we want to disable something, we want to set. Okay, so these are the very generic macros we can directly use in our code. So set, reset, GPIO pin set, GPIO pin reset. So what will be the meaning for that? Enable, disable. So generally we set the bits, reset the bit, okay, and that enable or disable something. So meaning is that if we will write enable, so that will be replaced by 1 value. Disable means 0. Same thing, set means 1, reset means 0. So that will be used as a macros we have defined here. So it may be used in our another file. So after this is the MCU specific file. I have written some code. This is not the complete peripherals. Okay, so the main important peripherals, some idea I have mentioned here. So like related to the GPIO. So in this way, we can define all the address or register address, all fields. Okay, and after that, we can create a that peripheral specific driver. So how we can create that? So related to the, we will create another file. So suppose we want to create a driver for not GPIO specific, not the MCU specific, but GPIO specific. So you can see we will create a two file in the same way. One is GPIO driver .c and another is GPIO driver .h. So first we will come from this GPIO driver .h, and now you can see we will define the GPIO related data information in this. Okay, so if we are working with the GPIO, so what type of operation is required, what things, what type of data is required. So we will define everything here inside this header. Okay, so this header will contain some definitions or macros, and the source file will contain the implementation. So you can see we have defined this now. Yeah, so you can see we will include the MCU related header first, because most of the things we will access from the MCU header file, base address, all these things. Okay, so we will include this header file in our code, this GPIO drivers, and after that we will define the things. So now you can see GPIO, what are the, so for each registers what are the possible values we have. Okay, so that actually will define here. So you can see for the GPIO, that pin configuration, so how the pin can be configured. So what are the fields we require to configure inside this GPIO pin? That is actually pin number, we need GPIO pin mode. What should be the pin mode? Actually, pin speed and pin output type. So all what are the registers we have for the GPIO? So that we will define inside this structure GPIO pin configure. Okay, and some possible mode we have will define with some label here. So like we want to set our GPIO pin to 0 value. Okay, so you have seen this GPIO mode. So in the registers, so we have 4 options. GPIO mode and this GPIO registers. So you can see this mode, input mode. So if you want to define the mode, so we need to set 00, then 01. So 00 means 0. This is represent to 1. If we will convert this into a decimal, so this represent as a 2, this represent as a 3. Okay, so what mode we actually want to define? So we have declared this as a macro. Okay, so this input mode, okay, 0. If you want to use as a output 1, if you want to use as a alternate function 2, analog function 3. Same we can define for other type. Okay, what is the output type? So output type we can define 00, that push pull mode and open drain mode. So based on the value you can give some label to understand easily. Okay, instead of value and actual address, here what we are doing actually, we are defining some label which we can directly call that label and we will directly use in our code. Okay, without writing this 0 1 or address things in the hexadecimal, all the operation, we will describe everything by some labels or names so that we can directly call. Okay, so like this we will set the pin number also. So instead of writing pin number like 0 1 2 3, we can define like this. So GPIO pin number 0, so it will be clearly represent that what is actually this 0 is representing. So this is representing pin number. Okay, so GPIO pin we have. So some GPIO pin handle structure. So how we will handle our pin? So we have created this one pointer inside this structure and another is pin configuration for each. So for each GPIO we need this one pointer for that and another is the configuration. So this is the structure actually. Okay, so this is another structure we have. Data type of the both is actually structure. Okay, so we can set all the that structure member field value directly from this. And after that we require the implementation of the functionality. So suppose if we want to read the data, if we want to write the data, so we will define the function for that. So first function is you can see this GPIO peripheral clock. Okay, so clock setup, this function is defined. That clock actually this is for GPIO. Okay, so we want to enable our clock or disable our clock, so that will be defined. So this is just a function prototype which is defined inside the header file. It will be implement inside the source file. Okay, so you can see this is just a definition of the function. So peripheral clock, we will get that GPIO port number, and this is enable or disable what we want to do. This GPIO initialization. Okay, so that first thing initialization, that will actually set the mode, all these things. So we need the which GPIO actually we want to set up, so that pointer we will get. GPIO read from input port, all function prototype we have written here. So now this file is done, and after that source file you can see. So all function which we have defined in the header file, now that is actually need to implement here. So you can see what we are including inside this is a header file for the GPIO. So that all definition are now included here. After that we will implement all the functions. So if you want to enable the clock for any specific GPIO peripheral, so you can see we can write the code like this. Okay, so we will get some value and enable or disable. Now we will check if this value is enable. After that we will check which port actually we want to enable. So if this our pointer value is related to this GPIO A, so we will directly call this. This function is already defined inside the header file. So this one h is true. Okay, so that we have seen this. Yeah, this one. Okay, this right. So I think we also okay, yeah. Let's see. So if we are including this file in this source file, so inside this header file we have already included the MCU specific file. So that function can also be accessed all these things. So here we can write like this. Okay, so we can directly call. So in this way we have defining the function. So now GPIO initialization, we want to initialize the GPIO, so we can set up all the things, like we can configure the mode by writing the code like this. Okay, we can set up the OPP type, or remaining things we can also write the code like this. Okay, so everything is defined, every functionality is defined inside the source file. Functionality is defined, labels are defined as a macros. Now after setting up of all these things, now when you will write a that application code, you no need to recall all the address, no need to read the document, all these things. You just uh, you can directly call the names. Okay, you can already call this function which is defined inside the header file. You can use the macros, you can directly call the macros. Base address is already defined, so instead of recall all the address value in the hexadecimal form, you can simply recall the names which is defined as a label. So after that, you can write directly your code with the help of this all drivers files, which is already defined. So this is the one time actually work. If you are working on any specific MCU, you can write your drivers. After that, you can write the code and directly call these functions. So this is called as a API. Okay, so this function we have written here, you can see this GPIO init. Okay, so in this function we will simply pass the port which GPIO actually which we want to initialize. So GPIO A or GPIO B or GPIO C, like this. We will pass this pointer field in this function. This function will actually set up, initialize the all required registers value, okay, in the one call. So you don't need to set up everything. But after that, you need to just call the specific function, and that function will perform all the tasks. So after so this is the way to develop the driver code for that any microcontroller. So now this is actually not completed. So otherwise, I'll will get. I wanted to give one demo to write the final code with the help of this driver code to just turning on the LED or something by the button or something. But still some part is pending, so it will not run actually. So that could not complete. But I hope you got some idea that how we can create the files. So maybe after in the next session I'll complete this, and then I'll give the complete demo after writing all these peripherals, how we can use that to write a application code. Okay, so final application code. So yeah, this is the structure for the drivers. So if you are using this HAL driver, so that hardware abstract layer, so that also contain these drivers files inside that. Okay, so it's the same driver files for the every peripherals. Okay, so what we are trying to do here, same way they have already done. So now if you know the full structure, you can directly use. Otherwise, you can also develop your driver. So if you know this skill, so definitely in this area, this is the very good skills if you know the driver development, understanding properly. Okay, so you can start this, start to explore this, how you can write the driver code for MCU. After that, so and when you will write a driver code for any specific microcontroller, you will also learn all the details of your microcontroller. Okay, so you will also learn the everything related to your hardware if you will write a complete driver code by your own. Okay, and you will also learn lots of things. So yeah, this is the things I have done today. So yeah, I could not complete So maybe next session I'll complete this and give the complete final demo. Okay.
Sir,
Yeah. Any query? Any specific query?
sir, after this code get completed, what are the things that we can achieve?
So what are the things after writing this code? When we will write this suppose we want to write a code to turn on the LED by push button. Okay. So now this is the application actually. Here we have some specific task. So if you remember that we have written the code for this. If you remember this code. So that in the previous example I have done this push button LED new code. Yeah, this one. So you can see we have write this complete code now. So we have defined all the registers and this base address for each registers, and after that we have set up all the things delay and this we have enabled the clock. Everything we have done from the base actually. We have defined everything from the address bases. But
Yeah, yes,
now
sir.
after defining all the things in our drivers, so we no need to do all these things. We will simply call the function. We will first thing we will include our driver file in our code. Okay. After that we will simply call the functions. So one function will perform all the tasks. So we will no need to define all these things. This is already defined in our driver. So we will directly use this. Okay, so the same task we can do in only 4 or 5 steps. We will write the 4 or 5 things and we will get our task done. So like HL tasks, HL code, where you just call a function, pass the value, and or your operation done. So same way you can write your code after that. Okay, without writing everything from the scratch.
Yes, sir. But sir, is it possible to have a user interface also for this?
No, that is actually development side, application development side. So they have actually designed some user interface. So that we cannot. If you know the application development things, then you can design. So what they are doing, they have just created some application and they have give some interfaces manually where you can set the things like which you are doing in your walkWe or here also. So you can set the pin by just clicking by your mouse. Okay, and after that it will automatically create the code. So that things is developed by the application developer, not the driver development. Okay, so that application development is there. So they have provided the user interface. So that things you will not get here. We are discussing some more harder hardware closure things, not the this user interface like this.
Yeah, yes, sir.
Okay, so that if so in this type of course, if you know the deeper knowledge, so that will be very good for you for the future. Okay, if you know the deeper knowledge like system level or hardware level knowledge, or actually what happened, they provide the abstract layer, so you just only use the functions but you don't know what happened inside the functions. So that things we are actually trying to do here. So what happened inside that function which we are generally used in our Arduino or in our HAL, how these functions are actually doing the task internally. So that we are trying to understand here.
Yes, sir.
Okay, so yeah, so you have got some idea maybe. So otherwise I'll complete this in next session with some demo. Okay, so
Yeah, sure.
maybe very less task is remaining to perform some task. So I'll complete this. So okay, so
Yes,
yeah,
sir.
this is the things today. So maybe next Friday or next to next, then we will discuss this. Okay.
Yeah, thank you. Very good session, actually.
Okay. Yeah. Thanks.
Thank you, sir. Thank you, sir. Good night, sir.
Yeah. Good night. Good night, everyone. Bye.
Yes.